So this video we're going to talk about magnetic dipoles, and this is covered in chapter 30-6 of the textbook. Alright, so a little reminder. So back when we were looking at electric fields, we looked at an electric dipole. So remember, an electric dipole was a positive and a negative charge, equal in magnitude, separated by some distance. And this is what the electric field lines from an electric dipole looked like. It's sort of a butterfly looking thing. Now, we recently talked about the field from a current loop. So imagine here, so on the right hand side, so you've got some loop of current. So you're kind of looking at the side view of this current loop. And this is what the magnetic field lines from the current loop look like. And if you look at this, so actually if you're far away, so if you're outside the current loop, the field lines from a magnetic current loop, the magnetic field lines from a current loop look the same as the electric field lines from an electric dipole. So that's why these are sometimes called a magnetic dipole. So a current loop is just referred to as a magnetic dipole. So the field from the current loop, and this is on the x, so this is from the Biot-Savart law, so is given by this expression over here. So, and remember, if you're very far from an electric dipole, so you can take a limit and you get an electric field of 2k times p, which was our electric dipole moment over the distance cubed. Now, if you're far away from a magnetic dipole, so and again, you take the limit here as your distance gets large and you wind up with an expression like this. So that means we can actually define, so remember for electric dipoles we defined an electric dipole moment, which was the charge times the separation distance. For magnetic dipoles or current loops, we can define a magnetic dipole moment. And we're going to use mu to stand for the magnetic dipole moment, and we're going to take the current I times the area of the loop, A. So if we have a circular current loop, well, the circular area is just pi r squared, and we multiply by the current I, and the direction, so this is a vector, so the direction is going to be perpendicular to the current loop. And to figure out, well, so if you have a circular current loop, it's going to be either straight up or straight down. So we're going to use the right-hand rule to give the direction. So if we've got a circular current loop, so you take your right hand, you wrap your fingers in the direction of the current, and your thumb is going to give the direction of the magnetic dipole moment. So then if we rewrite this, so the expression for the magnetic field far away from the magnetic dipole in terms of the magnetic dipole moment, you get the expression down here at the bottom. So the field is approximately mu naught over 2 pi times the magnetic dipole moment mu over y cubed. Right, and this actually starts to look quite similar to what we had for the electric dipole. So just one possible source of confusion, remember that mu is being used in a couple of different ways here. So we have our constant mu naught, the permeability of free space, but then you also have mu, which is the magnetic dipole moment. So those are two different things. Okay, so, well, if you have electrons or atoms, so first off, well, you look at an electron. Well, an electron is a charged particle and it has spin, so electrons have an intrinsic magnetic moment. And not only that, so now if you have an atom, so you can think of your electron as orbiting a nucleus, although quantum mechanics says it's a little more complicated than that, but we can still think of this orbit. So it's also going to have a magnetic moment due to its spin. So the total magnetic moment of an electron in an atom is going to be the magnetic moment due to the electron spin plus the magnetic moment due to the orbit. So, and just as a sidebar then, so for a charged spin 1/2 particle, like an electron, or there's another fundamental particle called a muon, so the magnetic moment, the intrinsic magnetic moment, depends on the spin and a fudge factor called g. And this magnetic moment mu is equal to this fudge factor g times the charge, the electron charge, over twice the mass times the spin vector s. And for most fundamental spin 1/2 particles, this factor of g is almost but not quite equal to 2.